Analyzing antiderivatives numerically and graphically. Consider that you know the derivative of a function. If we refer to the original function from which we got that derivative, we call that the antiderivative. So for example, consider that you know that the derivative of a function is 4x cubed. Then an antiderivative would be x to the fourth. Because if you take the derivative of x to the fourth, you get 4x cubed. So when we refer to the original function, when we're talking about derivatives, we can now call that the antiderivative. Now, remember, the fundamental theorem of calculus starts by looking at the area under a derivative function. We have a definite integral, which tells us the total change in the original function. We look at the derivative, and we look at the area under the curve between points A and B. Now, the area under the curve is equal to the change of the original function. So for example, if we had a velocity derivative, and we were looking at the area underneath the velocity curve, that would be the same as if we had the position function and we looked at how our position changed between 2 points. The area under the velocity curve would give us that same amount of change. It's another way of analyzing information from a function or a graph. Now, when we look at the right-hand side of the fundamental theorem, this is talking about the original function or the antiderivative of the derivative we were looking underneath. This can be written in two different ways. The first line, you'll see that we have capital F prime of x. However, sometimes in math, we also use the notation where we're going to use lowercase f to represent the derivative and uppercase f to represent the antiderivative. We'll have to look at the context of the problem to determine which type of notation is being used. Either way, we need to remember that the fundamental theorem of calculus tells us that the definite integral of the derivative function, which is the area under that curve, is equivalent to looking at the change between 2 points on the antiderivative. We're going to be able to use this to enhance the types of things we can do with the fundamental theorem of calculus. So instead of just talking about how much the original function changes, we can get actual values on the original function if we have a starting point. So let's see how we can use the relationship between the derivative and the antiderivative to learn more about the functions we're looking at. Example 1. Suppose that little f of t is the derivative of capital F of t, which is 2.2 raised to the t. Suppose that we also know the value of the antiderivative at 0 equals 3. So we know the value on the original function at 0. We want to use the fundamental theorem to find values for f of b, the original function, at the points 0.25, 0.5, 0.75, and 1. So we start by thinking about what we know about the fundamental theorem of calculus. Remember, the fundamental theorem of calculus will tell us how much we change between 2 points. One of the points that we're given that we want to consider here is x equals 0. Now, that's going to serve for our lower bound of what we're looking at because the values of v that we're looking at are going to be higher than that original number. So we start by setting up a general equation for the fundamental theorem of calculus, which looks like this. Here we see that the definite integral from 0 to b of 2.2 to the t dt is equal to the antiderivative at b minus the antiderivative at 0. We do know some information. We know that f of 0 has a value of 3 because that was given to us in the setup. But here, since we're going to be putting in multiple values for b, what we can do is we can solve this equation for f of b. We can do that by taking the f of 0 and adding it to the left-hand side. Doing that will give us an equation that looks like this. So now, if we want to get the various values for f of b, we can plug in each of the required upper bounds, 0.25, 0.5, 0.75, and 1, to get the value of f of b. So let's see what that looks like. If we wanted to find the value of f of 0.25, so that's the dependent value on the original function when t equals 0.25. The fundamental theorem tells us that'll be f of 0, our original amount that we started with. Again, that value is 3, given to us in the setup, plus the amount of area under the curve from 0 to 0.25. Because again, that tells us how much the original function changes between 0 and 0.25. So remember, f of 0 equals 3, and then we'll add on that change. To calculate that change, we'll use a calculator or a computing tool to figure that out. When we do, we find that that value is equal to 0.2763 when we calculate the integral. So we add the 3 to the 0.2763, and we get 3.2763. I chose here to round to 4 decimal places because there was nothing in the instructions about how I should round. Be careful when you're answering problems to see if the problem asks you to estimate to a certain decimal point. We can now follow the same plan to figure out the values at b equals 0.5, 0.75, and 1. So let's look at the next one. So if we want the value at 0.5, we then need to adjust our formula. So our b, the upper bound, becomes 0.5. So f of 0 is always going to be 3. That's a normalized amount that will always stay the same. So we have 3 plus the amount we change between 0 and 0.5. So again, we'll plug that in to see what that change will be. Plugging this in will give us a value for the integral of 0.6129. So that tells us that the value of the antiderivative at 0.5 is 3.6129. Let's move on to 0.75. So to calculate the value at 0.75, we have f of 0 plus the integral from 0 to 0.75 of 2.2 to the t. So remember, that integral is going to tell us how much our original function changes between 0 and 0.75. Plugging this in, we will get 3 plus 1.0228, which gives us a value of 4.0028. So finally, we want to look at the value f of 1. So again, we're going to plug in a 1 for our upper bound of our integral. Our new equation looks like f of 0 plus the integral from 0 to 1, 2.2 to the t. So again, plugging in a value of 3 for f of 0, that's our initial amount, and then adding on how much our function changes from 0 to 1 will give us 3 plus 1.5220. That's the value that I get from computing that definite integral. Adding those together gives me 4.5220. So what kind of information does this tell us? If I wanted to graph the original function, my antiderivative, I would have some points that I could plot. For example, when t equals 0.25, my y value would be 3.2763. When my t value is 0.5, my y value is 3.6129. When my t value is 0.75, my y value would be 4.0028. And when my t value was 1, my y value would be 4.5220. I can see here that my original function is increasing from 0 to 1. And that makes sense because if I was to draw 2.2 to the t, all of the area would be above the x-axis. So these are relationships we've explored before that we're starting to apply here to compute actual values. Now, we can also do this graphically. So let's look at the next example. Example 2. Suppose that f of t equals capital F prime of t is given in the graph below. So again, derivatives can either be written as lowercase f or capital F prime. So we have the derivative in our graph below. We also know that on the original function, that the antiderivative has a value of 4 when x equals 0. Think of this as an initial starting amount. We always need that in order to do our analysis. We want to use the fundamental theorem to find values on the antiderivative function at 1, 2, 3, 4, 5, and 6 based on what we know from both the graph and our initial information. So remember, the fundamental theorem can be set up with an upper value of b to represent all the different b's we're going to be calculating as we go. So what does that look like? This is very similar to the last problem. We start by setting up our general fundamental theorem here. We know that the integral from 0 to b of the derivative will be the antiderivative at the upper bound minus the antiderivative at the lower bound. Here, we're going from 0 to b because f of 0 is information we're given and also where we start our graph here. And then we're going to go up to the different values of b. So 1, 2, 3, 4, 5, and 6. So again, since we're looking for various values of f of b, we want to rearrange our equation by taking this f of 0 and adding it over to the other side, therefore solving for f of b. So f of b equals f of 0 plus the integral from 0 to b of little f of t dt. So let's remember what these things represent. So capital F of b is the value of the function at b of the antiderivative function. And that's equal to the value of the antiderivative at 0 plus the amount that that function changes from 0 to b. Now, last time we were able to compute the change by plugging functions into a computer. However, here we have a graph, so we have to remember what we know about how the graph relates to the definite integral. So let's look at each of these values. We start by looking for the value f of 1 when b equals 1. So the antiderivative value at 1 will equal the antiderivative value at 0 plus the integral from 0 to 1 of little f of t dt. We know the value of f of 0 because that's given in the setup. That has a value of 4. Now, to evaluate the definite integral, we need to compute the area under the curve. Now remember, the area under the curve is the area that's bounded by the function and the x-axis. If the area is above the x-axis, we count it as positive. If it's below the x-axis, then we count it as negative, because if it's below the x-axis, that's telling us that the original function was decreasing. So if we look at what's happening from 0 to 1, which is the integral that we're evaluating here, we see that that area is represented by a rectangle. Here, that area is a 1 by 1 rectangle. So that gives us an area of 1. So that means we're going to take the value of f of 0, which was 4, again from our initial information, and add on the change, which is the area we found to be 1. Therefore, the value of the antiderivative at 1 will be 4 plus 1, which equals 5. So again, that tells me that when the t value on the antiderivative is 1, the y value has to be 5. We're going to do the same thing for each of the other values of b. So for f of 2, now we have to consider all the area between 0 and 2. Our equation looks like this. We can see the part that changed from the prior equation is the top part of our bound. So we know that we're starting with f of 0, that value is 4, but then we have to add on how much the function changes from 0 to 2. We already know how much the function changes from 0 to 1. We computed that in the last step. But now we also need to know how much we change from 1 to 2 so that we can look at the total area that's changed from 0 to 2. So you can see here that the area from 1 to 2 is a triangle. And if we were to compute the area of this triangle, we would do 1/2 base times height. The base here is 1 unit long because it goes from 1 to 2, and the height is 1 unit high. So 1/2 times 1 gives us an area of 1/2 for our triangle. So that means that we're going to take f of 0 and add on all the area change from 0 to 2. So we have our initial value of 4 plus an area of 1, which covers the area from 0 to 1, plus the area we just found of 1/2. And if we add those all up, we get 5.5. So remember, the 4 is the initial value, the 1 is the area from 0 to 1, and the 1/2 is the area from 1 to 2, which gives us the whole coverage of 0 to 2, which is what our integral asks us to find. Now, if we do the same thing for 3, for f of 3, we're going to continue the same process where we're adding on our areas. So let's see what our equation is going to look like. Again, the major change is the upper bound of our definite integral. So for the upper bound of our definite integral, we now have 0 to 3, which means we need all the area from 0 to 3. Well, we already have all of the area from 0 to 2 from before. However, now we have to incorporate the additional area from 2 to 3. So from 2 to 3, you'll see that we again have a triangle. And that triangle has a base of 1 unit and a height of 1 unit in the negative direction. When your area is below the x-axis, we count that as negative when we're talking about definite integrals. So this area is 1/2 times 1 times 1, but negative. So this area is negative 1/2. So when we talk about all the area from 0 to 3, when we're talking about our integral, we have the area of 1, which was from 0 to 1, the area of 1/2, which was 1 to 2, and then we have to add on negative 1/2 to represent the area from 2 to 3. So adding up all our values, we get that the value at 3 on the original function will have a y value of 5, because again, it's f of 0, the original amount, which is 4, plus 1 plus 0.5 minus 0.5. Now to calculate f of 4, we're going to continue the process the same way. Same thing for 5 and 6. So for f of 4, f of 5, and f of 6, we start with the same general equation where the upper bound changes to 4, 5, and 6 respectively. We all know that we're going to start with the value of 4 and then add on how much the function has changed between 0 and the upper bound. Well, we already know that we have to include all the changes that we've talked about so far. So the change from 0 to 1, the change from 1 to 2, the change from 2 to 3. So next we'll look at the change from 3 to 4. The change from 3 to 4 is what we're going to be looking at for the next value for f of 4, but will also be part of the calculation for f of 5 and f of 6. So when we look at the area under the curve between 3 and 4, we see that again, we're going to have a rectangle. So we have a base of 1 and a height of 1. So we have a 1 by 1, and 1 times 1 is 1. So that area, again, because we're talking about definite integrals and because we're below the x-axis, will be negative. So to go from 3 to 4, we have to subtract off 1. Because this process is cumulative as we move from left to right, we can do the minus 1 from all of our functions below. However, when we're calculating f of 4, that's the last calculation we need to do because we've now added in all the areas from 0 to 4, so crunching those numbers gives us 4. To calculate f of 5, we also need the area from 4 to 5 to be included. That's the one that's still missing. From 4 to 5, we can see that it's again going to be a rectangle. And again, because that rectangle is below the x-axis, we count it as negative. And again, it's a 1 by 1. So that means that the area from 4 to 5 will be negative 1. So we need to add that to our calculation for both f of 5 and f of 6. For f of 5, that'll be the last piece we need. So f of 5 equals 3, because again, we took f of 0, our starting point, which was 4. We added on all of the areas between 0 and 5, where anything above is counted as positive and anything below is counted as negative, and when we solve for that, we get 3. So if we were to be graphing the original function, when our t value equaled 5, our y value would equal 3. Finally, to calculate f of 6, we need to find the area from 5 to 6. That's the piece that we're missing. We have all the other areas we need before then. So from 5 to 6, you'll notice that again, we have a triangle. And for a triangle, we're going to have 1/2 base times height. So here, my base is 1 unit long, and my height is 1 unit long. So 1/2 times 1 times 1 is going to give me 1/2. And again, because it's below the x-axis, I count it as negative. So I have to subtract off from my final calculation here, which is going to give me a f of 6 value of 2.5. So let's remember some of the other connections that we know about derivatives and original functions. I'm going to point them out here, and then we'll write them down again more formally. So remember, when your derivative is positive, so above the x-axis, that tells us that the original function is increasing. We learned about those relationships prior to this. When your original function is decreasing, the derivative is negative. So here, since we have a picture of the derivative, we're looking at when the function is above and below the t-axis. We see that our function is above the t-axis from 0 to 2. So that means when we're computing values between 0 and 2, we expect the y values to be increasing. Now, this holds true. At 0, the y value is 4. At 1, we found a y value of 5. At 2, we found a y value of 5.5. So those y values are going up. 4, 5, 5.5. Those are increasing. When our derivative is below the t-axis, like it is here from 2 to 6, we expect our function, the antiderivative, to be decreasing. And if you look at the y values between t equals 2 and t equals 6, you can see that those y values are indeed decreasing. 5, 4, 3, 2.5. Those are decreasing values, which corresponds directly with the fact that our derivative was negative or below the t-axis. So let's remember exactly what those relationships were and see how that can help us be a little more careful with the work that we're doing. So remember, if f of x is increasing on an interval, then the first derivative is positive on that interval. This is true for a point as well as an interval. And the way we talked about this before is imagine that you have some function, f of x. Now we're talking about where this function is increasing. So let's pick a point where this function's increasing and look at the derivative. So let's pick this point right here. Our function is surely increasing there. Remember that the derivative tells us how much that function is changing at that point. And the way we do that is by finding the slope of the tangent line. So the slope of the line that touches right there is surely going to be positive because it's an upward sloping line. So that's why our first derivative is going to be positive whenever our function is increasing. We could draw in tangent lines a couple different places where our function is increasing and see that the slopes are always going to be positive there. So this is important because when we start with a derivative graph, if it's positive, that tells us that the original function was increasing. This relationship works in both ways. And the more careful and correct we want to be about drawing and talking about antiderivative means we need to use the information we know about the derivative to inform us when talking about the antiderivative. Similarly, we know that if the original function is decreasing on an interval, that the derivative is negative on that interval. So again, we have some picture, and if we pick a place where we're decreasing, like here, this is the original. If we want to talk about the derivative, we're looking at the slope of the tangent line. So here, the slope of the tangent line is going to be downward sloping. If we draw on the tangent line on any of the places that we are decreasing, we will see that the slope is negative. So again, we have this relationship that if the original function is decreasing, the first derivative is negative, which means if we're talking about the derivative to inform us about the original function, that anytime the derivative is below the x-axis, that will inform us that the original function was decreasing. Finally, we know that if the original function is constant, which means it's not increasing or decreasing, it could either be flat or at a place where we're turning around, then the derivative will equal 0. So that happens when we're changing from increasing to decreasing or decreasing to increasing. And that looks like this. So again, if our derivative equals 0, which is the slope of a horizontal tangent line, that tells us that we are likely at a place where our original function is changing from increasing to decreasing or decreasing to increasing. Let's use these graphical relationships to help us understand a little bit more about how the derivative can inform us about the antiderivative. Example 3. Consider the derivative of f of x given in the graph below, so f prime of x. Additionally, suppose that we know that f of 0 equals 1. Use this information to sketch f of x and discuss the local maximum and minimum of f of x. So again, we're starting with a picture of the derivative, and we want to use that to inform us about the antiderivative or the original function. So what we're trying to sketch here is the original function. Now, in doing this, we have to put together a lot of the pieces and things we've been talking about. Here, we know that f of 0 equals 1. So that's a functional value on our antiderivative. So when x equals 0, y equals 1. Now, we can use the same process that we did in the last problem to inform us about some of the values that are going to be on the antiderivative. So for example, we can look at the area between 0 and 1 to figure out the value of the function at 1. So here I have a triangle, and the area of this triangle is going to be half, because the base is 1, the height is 1, so 1/2 base times height is half. So what that tells me is that I'm going to increase by half when I move from 0 to 1 on the x-axis. So the value at 1 is going to be the value at 0 plus the integral from 0 to 1 of f prime of x dx. We said the value at 0 is 1, plus we said the change is half. So that means I'm moving to 1.5. So that's right about here. Okay. If I also wanted to plot some more values, I could look at what was happening up to, say, 3. It's a good logical place to look at this. So f of 3 will be f of 0 plus the integral from 0 to 3 f prime of x dx. Well, we know that f of 0 is 1. Then we know that I have to add the 0.5 for the area between 0 and 1. But now I have to add 2 more areas, the area between 1 and 1.5 and the area between 1.5 and 3. The area between 1 and 1.5, I'm going to do in red here. So the base here is half, the height is 1. So I have half times 1 times half. So when I multiply those together, I get 1/4. Since it's above the x-axis, I'm going to add it on, so 0.25. But then I also need the area from 1.5 to 3. So again, this is another triangle. And in this triangle, I'm doing 1/2 base times height. The base is 1.5 units long, or 3/2 if you like fractions. And then the height is 3 units. So I'm going to be doing 1/2 times 3/2 times negative 3. So I will do that up above. So I have 1/2. My base, I said, goes from 1.5 to 3, or 3/2, times a height of 3. When I crunch all those numbers, I'm going to get 9/4, or if I turn that into a decimal, 2.25. But I have to remember that this area is below the x-axis. Since it's below the x-axis, that means I have to count it as negative. So when I put it in as part of my calculation, I have minus 2.25. So when I crunch all those numbers together, 1 plus 0.5 plus 0.25 minus 2.25, I'm going to get negative 0.5. So again, when my x value on the antiderivative is 3, the y value is negative 0.5. So right over here. Okay. So I know now, looking at this, I'm going to have to somehow turn around, right? And then if I want another value, I may consider what's happening at, say, 6. That seems to be where my graph ends. So what I notice here, I'm going to be a little bit sneaky about this, but what I notice here is that the area from 3 to 4 is the same as the area from 4 to 5, right? They both have a base of 1 and a height of 3. So I'm going to do that calculation kind of all at once. So 1/2 base times height is going to be 1/2 times 1 times 3. So that's going to give me 1.5. So when I'm below, it's negative 1.5. When I'm above, it's positive 1.5, which means that when I get to 5, the change between 3 and 5 is going to be 0, because I lost 1.5 and then I gained 1.5, which means I'm in the same place that I was at 3. But then when I get to 6, I notice that I'm going to have to add on some more positive area. So I know I'm going to be going up from there. So to go from 5 to 6, I'm going to add on another 1.5 from where I was. So that's going to bring me all the way up to 2. So I can calculate any of the values I want on this function. I wasn't specifically asked to find out what was happening at 1, 2, 3, 4, 5. I picked some that were convenient. You may pick different numbers, and that's okay. But how do I take these points and figure out what my graph looks like? How do I know what's happening between the points? Well, that's where the graphical analysis that we talked about before this comes back into play. I know that when my derivative is positive, as in above the x-axis, that my function needs to be increasing. So if I look at the first place where my graph is positive, I see that between 0 and 1.5, that my graph is above the x-axis on my derivative. And that tells me that the original function, or the antiderivative, has to be increasing from 0 to 1.5. So when I think about connecting my points here, I think about where 1.5 is. I have to be increasing until 1.5. After that, from 1.5 until 4, I'm decreasing. I'm moving in the downward direction, and I'm going to be decreasing all the way until I get to 4, because that's where the area is below the x-axis. So 4 is over here, so I'm going to turn myself around and decrease until 4. I unfortunately didn't calculate the value at 4. I could go back and do that, but I'm just trying to get a rough sketch here. But then from 4 to 6, my derivative is again above the x-axis, which means I need to be increasing after 4. So it's not pretty, right? But I do know where I'm increasing and where I'm decreasing. And if I look to answer the second part of the question, I now have a little bit of an idea where the maximums and minimums are going to happen. So on the original function, notice that I have a maximum at 1.5 and I have a minimum at 4. It's not a coincidence that those are the points where we changed when we were above and below the x-axis on the derivative. Remember, local maximums and local minimums tend to happen at critical points. And critical points happen when your first derivative is 0 or undefined. So my first derivative was 0 when I changed from above the x-axis to below, so at 1.5 and at 4. So when I graph this, I can see that that corresponds directly to my local max and min on my f of x graph. Now, it would be really nice if I had a little bit more information about what the shape of the graph looked like. I now remember increasing, decreasing. I'm able to find some points using the fundamental theorem, but we have one more relationship that we can apply here that we've learned before that will help us translate our graphs to talk about antiderivatives. And that relationship has to do with the concavity. So remember that if your first derivative is increasing, then you know that your second derivative is going to be positive on that interval. And if your second derivative is positive, that tells you that the original function is concave up. If f prime of x, or the derivative, is decreasing, then the second derivative is negative. If the second derivative is negative, that tells you that the original function is concave down. And if the first derivative is constant on an interval, then the second derivative is 0 on that interval, which may mean that you have an inflection point. So let's recap. If we have some information about the first derivative, we can look at whether the first derivative is positive or negative to tell us if the original function is increasing or decreasing. And we can also look at the first derivative and look at whether it's increasing or decreasing to tell us the concavity of the original function. So these relationships are critical to understanding how these types of relationships exist and how antiderivatives behave. So let's look at another example and see how these things all fit together. Example 4. Consider the graph of f prime of x below. The shaded areas are given, and f of 0 equals 3. Answer the following questions. So before we dive into the questions, let's just recap what we know from this graph. We have a graph of the derivative. The first yellow area, A1, is reported to be 3. The green area, A2, has an area of 6. And then the second yellow area, A3, has an area of 11. Our graph spans from 0 to 10 with markers at 1 and 5. So here, we want to make sure we understand these relationships to help us understand what we know about the original function based on this derivative graph. So the questions all ask about what's happening on the antiderivative, f of x. So before we do any analysis, we do know one point of information. We know that when x equals 0, y equals 3 on the antiderivative function. So let's see what else we know. Part A asks, on what intervals is f of x an increasing function, and on what intervals is f of x a decreasing function? So remember, whether or not the original function is increasing or decreasing is related to where the derivative is positive or negative. So we can see here that the yellow areas are positive. They are above the x-axis. So when your derivative is above the x-axis, the original function is increasing. Therefore, we're going to have an increasing function from x equals 0 to x equals 1, and from x equals 5 to x equals 10. Because again, that is where our derivative is positive or above the x-axis. We're going to have a decreasing function from x equals 1 to x equals 5, because that's where our derivative is below the x-axis, which tells us that the original function is decreasing. Part B wants to know, on what intervals is the original function concave up and where is it concave down? So remember, this is different. We are no longer looking at positive or negative, and instead we're considering where we're increasing and decreasing. So you can see that we're going to be decreasing from 0 to the line I just drew in. So we have to make an educated estimate about what the value is at that point. So you can see that from the 0 to 1 about how long that is. And we can see where the halfway point is between 1 and 5. So the halfway point is about here, right? So halfway between 1 and 5 is 3, and halfway between 3 and 1 is 2. So as an educated guess, I would say that this is at about 2.5. It doesn't have to be exact because the numbers are not labeled, but we should have a fairly good estimate. So from 0 to say 2.5, my function is decreasing, but it's decreasing again over here. So again, we're going to have to try to figure out roughly where that is, right? So halfway between 5 and 10 is 7.5, and the halfway mark is right around this A. And this is a little bit to the right of that. So I'm going to call this 8. Again, it's not exact. You might call it 7.75, something of that sort, but you should have a rough idea of when the increasing function hits the peak here and stops. So we're decreasing from 0 to 2.5 and from 8 to 10. If your derivative is decreasing, that means your second derivative is negative. If your second derivative is negative, your original function is concave down. So we're going to be concave down from 0 to approximately 2.5 and approximately 8 to 10. And again, we know that we're concave down because that's where your function, the derivative function, is decreasing. Now, similarly, we're going to be concave up when the second derivative is positive, and the second derivative will be positive when your derivative is increasing. So if I look at my picture here, I can see that my function is increasing from 2.5 to 8. So I'm going to be concave up from x equals 2.5 to x equals 8. So I have a lot of good information so far about my antiderivative. So part C asks, at what points does f of x have a local minimum and a local maximum? So we know local maximums and minimums happen at critical points, and critical points happen when your first derivative equals 0. So if I look at my function, I want to pay particular attention to where this function equals 0. So this will equal 0 whenever we cross through the x-axis. Now 10 is a contender, but since I can't see what's happening on the other side of 10, I don't know that it actually crosses through. So 10 is not going to be a contender for a local max or min since I don't know that it actually passes through to make the derivative equal to 0. So I have something happening at x equals 1 and something happening at x equals 5. Now, I know from part A that from 0 to 1, my original function was increasing, and then after 1, I was decreasing. So if my function is going up and then down, I can visualize that that's going to represent a local maximum. So if your first derivative changes from positive to negative, your original function has a local max. Similarly, what's happening at 5 is that To the left of 5, or what's before 5, my original function is decreasing, right? The derivative is negative, so the function's decreasing. And then after 5, the area is positive, so that means that my original function is increasing. So if you have a function that goes from decreasing to increasing, that visually represents a local minimum. So now I know that at 1, I have a local maximum on my antiderivative, and at 5, I have a local minimum. So now, part D, I'm going to compute some values. So for part D, I want to know what is the exact value of f of 1. So remember, in the original problem, I was told that f of 0 equals 3. That was back in the setup. So if I'm talking about fundamental theorem, I'm interested in what's happening from 0 to 1, f prime of x dx. The fundamental theorem says that that's f of 1 minus f of 0. This value is 3. So that means that f of 1 has to equal 3 plus the integral from 0 to 1 f prime of x dx, which equals 3 plus. Now the integral from 0 to 1 is the area that we're calling A1. And I'm told up in the right-hand corner that that area is 3. So I have 3 plus 3, which means that the value, f of 1, has to be 6. If I want to similarly compute f of 5 and f of 10, I can do f of 5 equals f of 0 plus the integral from 0 to 5 f prime of x dx, which is 3 plus all the area from 0 to 5. Well, the area from 0 to 1 was 3. And then the area from 1 to 5 is this green area called A2. That has an area of 6. However, I need to remember that since it's below the x-axis, it needs to be negative. So I have 3 plus 3 minus 6. So that equals 0. So f of 5 equals 0. For f of 10, I can do something similar. F of 10 will be f of 0 plus the integral from 0 to 10 f prime of x dx. F of 0 equals 3, and then the integral from 0 to 10 is all the area that I add up from 0 to 10. So from 0 to 1, I had positive 3. From 1 to 5, I had negative 6 because it was below. And then from 5 to 10, I have positive 11. So when I crunch those numbers, I get that f of 10 equals 11. So f of 5 was 0, f of 1 was 6. So I have 3 functional values on my antiderivative, plus I know where my function is increasing, decreasing, concave up, concave down, max and min. So putting this all together, I'm going to do part F, which is going to be to sketch a very accurate graph of my antiderivative. Okay. In order to sketch a graph of my original function, my f of x, I need to use all the pieces of things I learned from parts A through E. The easiest ones to start with are the things I just did in part D and E. Those were points. In part D, I found that f of 1 equals 6, which means that when x equals 1, y equals 6. I also found that f of 5 was equal to 0. So when x equals 5, y equals 0. And finally, I found that f of 10 equals 11. So when x is 10, y equals 11. So those are the points that I solved for. However, I also know one more point, which was given to me in the setup. I was told that f of 0 equals 3. That was given to me in the original problem, so I can plot that point. when x equals 0, y equals 3. So now let's remember what we learned in part A. In part A, we learned where my function was increasing and decreasing. So again, that corresponded to when my derivative was positive or negative. So I was increasing from 0 to 1, and again from 5 to 10. Now, that lines up with where my dots are. However, I also need to remember what the concavity is, so I know that when it's increasing, whether it bends upwards or downwards. So if I think about part B, I said that I was going to be concave down from 0 to 2. So if I'm increasing and concave down from 0 to 1, I have something that bends downwards, right? Now, I also know that I'm going to be decreasing from 2 to 5. But from 1 to 2, I still have to be concave down because I'm concave down from 0 to 2. So I'm decreasing concave down until 2. But then we saw from our analysis in part B that I'm going to be concave up from 2 to 8, roughly. So that means I have an inflection point roughly at 2. So now, after 2, I have to change how I'm bending, and I have to bend upward as I move along. And I have to do that all the way until I get to 8. So again, I should be decreasing from 1 to 5, which again I found because my derivative was below the x-axis. And that corresponds to what my picture looks like here. And I need to be increasing from 5 to 10 because the area above the curve was positive. I'm concave up until 8, at which point I start to bend in the other direction, and I'm concave down from roughly 8 to 10. So here's a picture that includes the points that I explicitly solved for, the intervals where I'm increasing and decreasing, but now I also know where I'm concave up and concave down, which makes my graph really, really reliable. A lot of information on this graph is very accurate. Now, it's not perfect. If I want it to be perfect, I need to solve for a lot more values, but this is a pretty good representation of what my antiderivative function will look like. So again, when you start with the derivative, you have a whole lot of information about the antiderivative based on what your derivative is doing. We started by explicitly calculating values using the fundamental theorem, and then we moved into analysis of what we know about the antiderivative using graphs. All of this ties together this notion of the antiderivative and the fundamental theorem of calculus.